All right, friends, we are on page 105. Your phone should be already away, and you should have your book out and open to page 105. And today we are looking at enthalpy. That's a new word, okay? For the purposes of Chemistry 11, enthalpy can be thought of as the chemical potential energy. That is not the true definition of enthalpy. But once again, just like heat isn't really kinetic energy, enthalpy isn't really the chemical potential energy. But I'll read you the definition and you can decide whether you like it or not. Enthalpy, a quantity defined by the relationship H equals E plus PV. The enthalpy change delta H for a reaction that occurs at constant pressure is the heat evolved or absorbed in the reaction delta H equals QP. Did we like that? No, I thought not. So we're going to think of it as the chemical potential energy, okay? So we run out of the symbol E stands for energy, so we cannot use an E for enthalpy. So we just end up grabbing a letter from the middle of the word, that H there. That H is going to stand for enthalpy. Enthalpy is represented by the letter H, and H is essentially the chemical potential energy, okay? Now, normally when we are looking at enthalpy, we're looking at the change in enthalpy from reactants to products. So just like last day, we did some potential energy diagrams and we looked at the change in the potential energy. This is just, we're just going to add in the word enthalpy, okay, along with that change in potential energy. And you guys are familiar with change in being represented by delta? How many people have seen delta to mean change in? Okay? If you don't know, delta means change in. And delta is a Greek letter, and it's just represented by a triangle, all right? So change in enthalpy is delta H. So reminding ourselves, in an endothermic reaction, kinetic energy is transformed into potential energy. So what's going to happen is that the potential energy is going to increase. Okay, the potential energy increases. And because we are basically saying that enthalpy, which is H, is the potential energy, the chemical potential energy. If potential energy is increasing, then enthalpy is also increasing. And if something is increasing, its change is positive. Okay? So we would have, for an endothermic reaction, delta H would be a positive value. In an exothermic reaction, we're taking some potential energy and we're transforming it into kinetic energy. So the potential energy is going to decrease and the kinetic energy will increase. If the potential energy decreases, remember potential energy and enthalpy are essentially the same thing. So if potential energy decreases, then enthalpy decreases. And if something is decreasing, its change is negative. Okay, so the change in enthalpy is negative. So for an endothermic reaction, change in enthalpy is positive. An exothermic reaction, change in enthalpy is negative. And we don't usually say change in enthalpy. We usually just say delta H. Okay? So when I say delta H, that just means change in enthalpy. So we're going to take a look at what we mean by the heat term, because you'll often hear things referred to as the heat term. If we have some gasoline and it burns, what type of reaction is it if gasoline is burning? That is combustion. Okay, and gasoline is mostly octane, C8, and then H, twice 8 is 16 plus 2 is 18. Who is the other reactant in a combustion reaction? Oxygen. O2. Everybody tell me, who are the two products of a combustion reaction? CO2 and H2O. Okay, so that's just a little review of that part of the unit. We actually have the reaction written down here, and it is balanced for us already. Let's think about any combustion reaction. Are combustion reactions endothermic or are they exothermic? Are they absorbing heat or are they releasing heat? Oops, wrong way around. Burning. Yes. It's going to release heat. You can feel it come out. Yes? If you've got anything burning and you like hold your hands up here and be like, oh, I feel that heat coming out. Okay, so the heat is being released. So yes. No. So combustion is exothermic. So the heat is exiting. Because it is exothermic. So what we've got then is we've got our reactants. The reactants have a higher enthalpy. They have a higher chemical potential energy. The products have a lower enthalpy, which is a lower chemical potential energy. If we were to graph this, do I have a graph coming up? If we were to graph this, what goes on the x-axis? That's the direction of reaction. You could also call it the progress of the reaction. What goes on the y-axis if we're graphing potential energy? Potential energy. So we are told that our reactants have a higher enthalpy and our products have a lower enthalpy. So should I start my graph high or should I start my graph low? Reactants have a higher potential energy. Products have a lower potential energy. Should I start my graph high or low? High, thank you. So these are our reactants. I'm just going to put R for reactants. I'm going to put P for products. Okay, we have the reaction takes place, and then we have our products, which are lower. And what is the unit of potential energy? We're going to write it as kilojoules per mole. Okay, kilojoules per mole. Now what we're going to do is we're going to look and we're going to say, in our graph, if I draw a dashed line there, and I start at the reactants, and I finish at the products, your arrow should start at the reactants and finish at the products. What's with that R? When you draw that arrow, that is going to show you the sign of delta H. It's going to show you the sign of the change in enthalpy, whether change in enthalpy was positive or whether it was negative. Okay, so we're going to label this arrow delta H. That is our change in enthalpy, our change in potential energy. So in this case, the arrow goes down. The potential energy is going down. Therefore, delta H is negative. Okay. Now let's go back up and look. We've got this heat here. Okay. That heat is some amount of kilojoules per mole. Yes? And you'll notice that written beside it is a plus sign. That's because it is a product. Okay? Anytime I have a product, if I had CO2 and H2O, I would write CO2 plus H2O. Okay? I wouldn't write CO2 minus H2O because the reaction is producing H2O. Okay? So I'm not sure I'm phrasing this very well. Let's just say that this value here was, I don't know, let's say it was 31. Let's just pretend. 31 kilojoules per mole. That's our heat term. Delta H, remember delta H was negative, yes? So the change in enthalpy is negative 31 kilojoules per mole. We have 31 less kilojoules of energy stored in our chemicals. Did that make sense? Kind of. How are we feeling about that? It's coming out, it's being released. We started higher, we finished lower. We don't write it as negative, but it is, the change is negative. So if I said, how much did it cost you to buy that chocolate bar? You might say, it cost me $2. Yes? Cost me $2. What was the change in your bank account? Negative $2. Okay? But you wouldn't say, what was the cost of the chocolate bar? Oh, the cost of the chocolate bar was negative $2. The negative is due to the fact that that is the change. Okay? So we don't put the negative in the equation. That's just kind of silly. Excuse me. So this heat has come out. Remember, this heat is kinetic energy. And so the particles move faster and the temperature increases. Okay, so now this is the official little diagram here on our next page. You can see here's our reactants up at the top. This should say kilojoules per mole. I would say when you are labeling the y-axis, don't label it as enthalpy, label it as potential energy, okay? And you'll notice also that in the previous diagram, I drew my dashed line over here and drew my arrow here, but it's totally okay to draw the dashed line for the reactants on the other side and to just start at the reactants and go down to the products for your arrow. Okay, so it doesn't matter which side you draw the dashed line on, totally fine either way. Okay, what you should be doing though is that the arrow should touch the line and the arrow should touch the line. So if I was labeling my delta H, I would want to see this. I would not want to see this. Do you see the difference? So you want your arrow, for your delta H arrow, to touch the line at the top and touch the line at the bottom, because otherwise you're like, oh, delta H is less than that. That's what it looks like. Yeah? Okay. So if delta H is negative, that energy had to go somewhere. We started with more potential energy. We figured ended with less potential energy. So where did that extra energy go? It came out as kinetic energy. And if it's coming out as kinetic energy, this is what thermic. Is it endothermic or exothermic? Exothermic. The kinetic energy exits the reaction. What's going to happen to your temperature? Is the temperature going to increase or decrease? We used to have less kinetic energy. Now we have more kinetic energy, right? Because it's coming out, we're releasing kinetic energy. Potential energy transformed into kinetic energy, and then the kinetic energy exits the reaction. So we have more kinetic energy than we did before. What is temperature? Define temperature for your neighbor. I might put this on your test. Definition of temperature. I'm not really big on definitions, like having you write them out, but this one I think is worth it. Temperature is a measure of the average kinetic energy. And if this reaction is exothermic and the kinetic energy is increasing, what is happening to our temperature? Temperature must I'll ask you again once you're done writing. So we have more kinetic energy. Potential energy went down, so kinetic energy had to go up. So we have more kinetic energy. So what's happening to the average kinetic energy? Average kinetic energy increases. So what happens to our temperature? Temperature increases. There are two ways to write a reaction to show that it is exothermic. Okay, one way is to place the heat term on the right-hand side. So you can place the heat term on the right side of the equation in the products. You can have a value, or it might just say heat, or it might say energy. It is being produced by the reaction. The other way to show in a chemical reaction that it is exothermic is to write the equation, and you can see the equation is exactly the same as it was before. Okay. But off to the side, we write the change in enthalpy. We write the delta H value. And this one, because it was exothermic, delta H is negative. Okay? So what we can do now is we can summarize that for exothermic, your graph go up or down for an exothermic reaction? It will go down. If you've got your reactants and you've got your products, where do the kilojoules go? Do the kilojoules go on the left side or the right side? They go on the right side. And if we have exothermic and we have reactants going to products, the delta H will be? Positive or negative? Negative. So you should know all of those things, okay? All of those all go together. If you have trouble remembering them, I want you to think about, you know, if you were going into, I don't know, the Vancouver Art Gallery or something like that, you know, usually if you go into a building like that or a museum, would you normally go up a set of stairs to get in, or would you go down a set of stairs to go in? You guys don't know? Have you never been to the Vancouver Art Gallery? Okay. Is it normal to enter a building by going down a set of stairs, or is it more normal to enter it by going up a set of stairs? More normal to enter by going up a set of stairs. So, if the stairs go down, you are exiting the building. So it is exothermic. Okay? And if you can remember that bit, then you can draw the graph, right? And if you can draw the graph, then you can figure out that you start at your reactants and you finish at your products. That means that enthalpy is decreasing, which means that delta H is negative. Yeah? And if delta H is negative, well, also, the heat term is exiting the reaction. Okay, so you should be able to relate, given any one of those three things, or those four things, 1, 2, 3, 4. Given any one of those four, you should be able to produce the other three. So if I give you number 4 and I say delta H is negative, you should be able to put the kilojoules into the reaction like in 3. You should be able to draw the graph like in 2, and you should be able to tell me that it is exothermic. If I give you this one, you should be able to tell me that delta H is negative. You should be able to draw the graph. You should be able to tell me that it is exothermic. Okay, so given any one of those, you should be able to tell me the other three. And now, guess what we're going to do? We just did exothermic. Now we are going to do endothermic. Because look at this, our heat is entering the reaction. Because where is the reaction taking place? The reaction takes place in the arrow. Okay, the arrow shows the reaction taking place. And we are told that these guys on the left have lower potential energy, and the guys on the right have higher potential energy. Where did that extra potential energy come from? We started low, we finished high. Where did that extra potential energy come from? What happened was we had some particles that were moving quickly. Before the reaction. And then during the reaction, kinetic energy is transformed into potential energy. And then after the reaction, that's where that extra energy came from. After the reaction, the particles will be moving slower because they lost kinetic energy. If you're planning on taking Chemistry 12, this is a key part of Unit 1. Okay? So if you're planning on trashing all your books at the end of the year, I would say keep this one, because keep this little section at the very least, because if you're planning on taking Chem 12, because this is definitely something worthy of review as you go through Unit 1. Okay? All right. So heat has been absorbed. Heat, which is our kinetic energy, is absorbed from the surroundings. It's those moving particles. And it is converted into enthalpy, which is our potential energy. And so here is our graph for that. What goes on the x-axis of our graph? Yeah, direction of reaction. This time I'm going to write progress of reaction just to be different, so you get used to seeing both of them. And what goes on our y-axis? Potential energy in unit is kilojoules per mole. Our reactants, we are told that our reactants have lower potential energy. So they're going to start low. Those are our reactants. And then we have our reaction. And then we have our products. And I wanted you to think about how you would draw the delta H arrow. How would you draw the change in enthalpy arrow for that? There's two places you could draw that change in enthalpy arrow. You could do it over on the right, delta H, or you could do it over on the left, delta H, and don't forget to make it touch each of the lines. Okay, and here is an enthalpy graph for this reaction. So we have our enthalpy, we have potential energy in kilojoules per mole. All right, you can see our reactants are lower, our products are higher. Delta H is going upward, so the change in enthalpy is positive. Okay? Where did we get that extra potential energy from? Kinetic energy is absorbed. Oh, that's great. Kinetic energy is absorbed, then transformed into potential energy. What type of reaction is this? Delta H is positive. Is this endo or exothermic? This is endothermic. Because look at our kinetic energy enters. So it's endothermic. And if it is endothermic, what's happening to the temperature? Is the temperature getting higher or is the temperature getting lower? Temperature's getting lower. Decrease. So in an endothermic reaction, the heat term is written on the left side. So that's going to be in the reactants side. And delta H is going to be positive. So here is our heat term, and delta H is positive. Hi.
Hello.
Who have we got here? Yunha, yes, she's here.
Awesome.
Thank you so much. And that one, it has sort of counselors, or sort of bodies, so you should go one time, stand. Yeah. All right, and now let's just do a little summary for endothermic reactions, just like we did for exothermic. So endothermic our graph would go up, okay? And you can think of this as the staircase goes up as you enter the building, okay? If you write your reaction, you've got your reactants plus your kilojoules goes to products. So the heat term is in the reactants. And if you write it with the delta H, you would have reactants goes to products, and the delta H is positive. Okay, so once again, you have 1, 2, 3, 4 things, and you should be able to mix and match between any of them and figure out them all from just one of them. Okay, so you have a little bit of practice here on these ones on pages 108, 109. Yes. Sorry, what was your question? It was just to go back up? Yeah, cool. I was hoping I had interpreted that correctly. Okay, so pages 108 to 109. And just grab a book. And last day we did 94 to 95. I know some people have already worked ahead of and have completed everything, but if you have not, you can do 96 and 97. Okay. And then if we have a little extra time at the end, I might teach you something new or I might not. We'll see how we're doing. Okay. We still have system and surroundings over the weekend. Depending on how much time you have to study next week or how much time you have to study on the weekend, I'll give you everything you need. Like I'll put up a study thing. There is extra stuff in Hebden, okay? So I will let you know what that is as well. I'll throw that up into our upcoming quizzes and tests, and I'll put it in the homework also, okay? So if you're wanting to work ahead, and get all reviewed over the weekend, you can do 6.3L, 6.4D, 6.4C. Okay.